Let's first talk about the diffusion model. The story begins with a drop of ink. As we all know, this is called a diffusion process, something you've learned in your early physics class. We all know that diffusion process proved that matter is made up of molecules. A group of molecules will gradually spread from their initial position until they permeate the entire space. At every moment, each particle moves in a completely random direction. This process is known as the Wiener process in mathematics and Brownian motion in physics. When Brown observed pollen grains in water, he noticed that due to the thermal motion of water molecules, the movement couldn't be uniform. At any given moment, the pollen experiences uneven forces, causing it to suddenly move in a particular direction. This direction keeps changing randomly, and as a result, the pollen bounces around. This is what we now know as Brownian motion. Let's visualize it by placing a bunch of pollen at a specific spot, like a point, a line, or even a smiley face, as they spread out independently. What do you notice? One obvious thing is that the original pattern gets distorted. No matter how the points were initially arranged, after enough time they turn into a jumbled mess. But this is not a coincidence. This chaotic distribution actually aligns with the Great Gaussian distribution, a classic result in probability and statistics. For instance, in one-dimensional space, if each particle moves randomly to the left or right by 1 unit, over time, the likelihood of their positions will fit the well-known bell-shaped Gaussian curve. The Galton board is a famous demonstration of this. Small balls randomly bounce left or right after hitting nails, and their final positions form a Gaussian curve. Isn't that fascinating? This directly connects to the central limit theorem in probability theory. This concept holds true in 2 dimensions as well. If each step is taken in a random direction, the resulting distribution will form a 2-dimensional Gaussian distribution. The diffusion process itself isn't surprising. It's just a natural mechanical process without purpose. In physics, studying diffusion is known as Langevin dynamics. However, in 2020, a groundbreaking paper creatively utilized the diffusion process to develop an image generation algorithm, now known as the diffusion generative model. If I had to sum up its key principle in one word, it would be time reversal. To understand how diffusion models generate images, imagine all particles starting from a single point, and then gradually spreading out into space. Now let's think in reverse. Where were they a moment ago? Since we are simulating this with code, we can track their movement and rewind time. Even though their paths differ, a common feature emerges: they generally move toward a central point. The further we rewind, the closer they return to their original position. This pattern holds true for other small areas too. So generally, if you take different random points and rewind time a little, you'll notice that all of them tend to move back toward their initial location. This demonstrates the difference between forward and backward diffusion. This process mirrors entropy decrease, turning noise into structure. At any moment, we can draw vector arrows for every position in space, indicating where the particles should have been a moment ago. Collectively, these vectors form a score function. The score function guides the particles back to their origin. Using mathematics, we can calculate the score function precisely. It enables us to direct particles from all over space toward their original shape. In simpler terms, by knowing the score function, we can reverse the diffusion process, reconstructing an image from Gaussian noise. Repeating this step-by-step process essentially runs time backward, forming order from chaos. Now you might ask, why does any of this matter for AI image generation? Well, let's dive into what makes an image realistic mathematically. A realistic image is simply a structured arrangement of pixels that follow specific constraints. In digital terms, an image is just a vector of RGB values. Each pixel is a numerical coordinate, and an entire image is a collection of these numbers. This collection exists within what we call pixel space. Most randomly chosen points in pixel space result in meaningless noise like TV static. Only a small fraction of vectors create meaningful structured images. These structured images lie on a manifold within pixel space. This idea is known as the manifold hypothesis in computer science. It suggests that real images exist within a constrained structure in pixel space. So, generating a realistic image means moving from random noise onto this manifold. The AI achieves this through deep learning. Deep learning trains a neural network to predict the previous state of an image given its current noisy state. By training on thousands of real images, the model learns the score function, which guides the denoising process. That's why this approach is called a denoising model. By following this process step by step, we transform random noise into a realistic image, but image generation is only the beginning. What about video generation? Video is essentially a sequence of images, with an additional time dimension. AI models like Sora extend diffusion models into this time dimension, ensuring logical coherence across frames. The biggest challenge is long-range dependence, keeping objects consistent across frames. Before we end, let me mention an important mathematical concept that is useful in image processing and future studies: first and second derivatives. The first derivative, also known as the gradient, detects where an image changes the most, helping to find edges and shapes. The second derivative, often represented by the Laplacian, highlights regions of rapid intensity change, refining details and enhancing edges. If you found this video interesting and helpful, please consider subscribing. By the way, this is my first time making a video on YouTube.